If you've been alive on planet Earth, you've probably heard of paradoxes. Roughly speaking, a paradox can be defined as a statement derived from seemingly true premises and seemingly valid reasoning that nonetheless seems illogical or contradictory. Often, these paradoxes result from logical fallacies, mistaken assumptions, or simply the gap between formal logic and common sense. One set of such paradoxes was written in ancient Greece, more than 2,000 years ago, by a man named Zeno of Elea. Zeno was a believer in monism, the idea that the universe was one singular and unchanging entity, and had written roughly 40 paradoxes of plurality seeking to prove that concepts like space, time, and multiple objects existing at once are logically contradictory and therefore illusory. Many of Zeno's paradoxes have been lost in time, and only 9 remain, having been preserved by Aristotle and Simplicius of Cilicia. Today I'd like to talk about his 3 most famous philosophical arguments, how we can make sense of them through calculus, and their implications on mathematics and infinity as a whole. 1. The dichotomy paradox. Suppose I wish to walk 1 meter. To do that, I must first walk half a meter. But to do that, I must first walk a quarter of a meter. But to do that, I must first walk an eighth of a meter. But to do that, I must first walk a 16th of a meter, and so on and so forth. Zeno posits that the task of moving forwards requires an infinite number of subtasks, and an infinite number of subtasks cannot be completed in a finite amount of time. Therefore, motion itself is impossible. 2. The Achilles paradox. Imagine the ancient Greek hero Achilles racing a tortoise. Since Achilles is much faster, the tortoise is given a head start of 100 meters. But once Achilles travels that 100 meters and arrives at the tortoise's original position, the tortoise will have already traveled a little farther ahead. Then, once Achilles has reached this new position, the tortoise will yet again advanced slightly, and so on and so forth. According to Zeno, since Achilles is always chasing the tortoise's previous location, he will never truly catch up. 3. The arrow paradox. Imagine an arrow flying towards a target at a certain constant speed. The arrow, obviously, is moving. However, if you look at any single durationless instant of said movement, the arrow is perfectly still. Zeno argues that since time is composed of an infinite number of instants, and objects in motion are motionless at every instant, motion itself is logically contradictory, and therefore impossible. At first glance, these arguments seem surprisingly convincing, and for centuries philosophers and mathematicians alike have struggled with Zeno's paradoxes. Zeno's argument hinged on the concept of the continuum, that space is infinitely divisible and that there exists infinite points between any 2 other points, and also that these points are discrete, although that's not part of the continuum. The previously commonly accepted solution to the paradoxes, Aristotle's argument, that Zeno's point breaks down if you consider space and time to be discrete or countable infinities instead of continuums, itself broke down after the development of calculus in the 17th century. As we all know, calculus is a subject that depends heavily on the existence of the infinitesimal. Within that theoretical framework, Aristotle's idea of discrete space falls apart. So how does calculus reckon with Zeno's ideas? Well, to take the arrow paradox for example, it can be easily solved simply by defining instantaneous velocity using limits, aka the idea of the derivative. Using the derivative, we can show that position being fixed at one instant does not imply the velocity at said instant is 0. Now that that's settled, let's return to the example of the dichotomy paradox, in which we wish to walk 1 meter. The Achilles paradox is logically identical to the dichotomy paradox if you think about it, so I won't be covering it again. To do this, we must walk 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus ... meters. Although his original text has been lost to time, we can assume that, as the Internet Encyclopedia of Philosophy states, Zeno argues that movement is impossible for one of these 5 reasons. 1. There is too far to run. 2. There is not enough time. 3. There are too many places to go. 4. There is no final step. And 5. There are too many tasks. Argument 1 can be rebuffed readily by calculus. The infinite series 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus ... as we well know, is a series whose sum converges, and as a geometric series, one whose sum can be calculated as converging exactly to 1, a finite and thus traversable distance. Argument 2 can be considered roughly equivalent to argument 1. Since we are moving at a constant speed, the amount of time necessary to traverse a finite distance must also be finite. Argument 3, 4, and 5, however, are more subtle, and they too can be considered roughly equivalent. Though the distance we are to travel is finite, the number of distances we travel is infinite. So the question now is, can an infinite number of tasks be completed within a finite time? This is the concept of a supertask, and even today, its possibility is debated among mathematicians. Theoretically, if the sum of each of the task's times of completion converge to a finite sum, such an infinite series can be completed. Only by accepting that can Zeno's paradoxes be resolved. And this does check out on a theoretical and mathematical level. Just as 0.9999999 does not need to have a final digit to converge to 1, we don't necessarily need a final step to be able to traverse an infinite amount of distances in a finite time. But, on a philosophical level, things are more complicated. Take these two examples. Imagine a light bulb being turned on and off repeatedly. In the beginning, it's turned on. Then, after half a second, it's turned off. Then on after a quarter of a second. Then off after another 1/8 of a second. Then on after another 1/16 of a second, and so on and so forth. After exactly 1 second, an infinite number of switches will have occurred. This is known as Thomson's lamp, proposed by philosopher James F. Thomson in 1954, and it poses a strange question. After that 1 second, is the lamp on or off? The solution, obviously, is impossible to determine. Every time the lamp changes state, there is always another switch afterwards. There exists infinitely many on states and infinitely many off states, but no final state to determine the answer. And yet, according to mathematics, in the same way Zeno's paradox is resolved, this supertask is indeed possible to complete. Here's another example. Suppose we place 10 balls in a vase, numbered 1 through 10. Then we remove ball number 1, and afterwards we place balls 11 through 20 into the vase and remove ball number 2. And then we place balls 21 through 30 into the vase and remove ball number 3, and so on and so forth infinitely. And of course, these operations, just as in the Thomson's lamp example, are happening at a half, a quarter, an eighth, and so on and so forth intervals. At first glance, the answer seems obvious. Every step adds 10 balls and removes only 1, for a net increase of 9 balls each time. Since the process repeats infinitely many times, shouldn't there be infinitely many balls left? But, if you think about it, every single individual ball is eventually removed. Ball 1 is removed during the first step, ball 2 is removed during the second, and ball 1000 during the 1000th. No matter which specific ball you choose, there exists some step at which it leaves the vase, no matter what. So, after this supertask is completed, shouldn't there be no balls left at all? Both arguments seem perfectly logical, and yet they give utterly contradictory results. This same understanding of infinity that calculus operates on, and that we've been relying on, simultaneously makes for all these logical contradictions. What really fascinates me is that these questions trace all the way back to a philosopher standing in ancient Greece over 2,000 years ago. Back then, Zeno had no idea that his paradoxes would one day help illuminate the foundations of calculus itself, the concepts of limits, derivatives, infinite series, the continuum, and so on. His arguments forced mathematicians and philosophers alike to confront uncomfortable questions about infinity that could not be ignored.